Okay, good morning, folks. My name is Dermot O'Dwyer. I'm one of the members of staff here in the School of Engineering, and I'm going to give you a talk this morning, a very brief introduction to civil engineering. Now, I realise that some of you sitting there may be more interested in mechanical or electrical engineering or computer engineering. So a lot of what I'm going to say also applies to engineering in general, because we pride ourselves here on the nature of the course that we have, which has sort of 2 years common. That means that when you're going through the degree in Trinity College, you get a good broad exposure to all the different streams of engineering in the first 2 years, and then you get a free choice after that. But even after that, when you're out working as professional engineers, you'll find that you won't necessarily fit neatly into the box of mechanical or civil or electrical. You'll probably see as I go through and start describing civil engineering, you'll see that it's going to encompass sort of areas we work in, encompass all the sorts of skills, say, you might need in mechanical engineering or electrical engineering. So for example, at one stage I worked as a railway engineer, so I had to know about mechanical engineering and electrical engineering. I would have been working on projects with engineers from a wide range of different disciplines. But specifically, I'm going to talk to you about civil now. But just to say, it should still be giving you a flavour of the engineering environment in general. Now, first of all, a plug for engineering in general. If you're looking for a career where you really can make a difference on a sort of global scale, I would recommend engineering, because it's a profession where you have a profound impact on the environment in which you live. Either as a particularly as a civil engineer, we're responsible for providing bridges, building the ports, the airports, providing fresh water, dealing with waste. And you get a great sense of achievement, because when you finished a large project or been involved in a large project, you actually have something that's left, that's there, that's permanent, that's probably going to last for most of your lifetime. As well as that, when it comes to actually making having a real impact on the living conditions of people, providing fresh drinking water, dealing with waste, that has a huge impact, particularly in developing countries. So more lives are saved in developing countries through providing shelter, particularly providing fresh water and putting in treatment works, than, say, even sort of careers like medicine. So it's a very, very important job, and also there's great job satisfaction. I'd ask you to go out and talk to people that you know, maybe older brothers or sisters who've gone through engineering. Talk to your parents, friends. Find people who are in the engineering profession, and whatever they might give out about, most engineers find their jobs interesting, and that is a real plus. Now, within civil engineering, the term civil engineering originally came about to sort of distinguish civil engineering from military engineering. There were originally only two types: engineers who worked with the army building fortifications or knocking down fortifications, depending on what mode the army was in, and everything else. Everything else was civil engineering. So civil engineering still has a very, very broad base. So I'm going to go through some of the specialist areas within civil to sort of give you an idea of the different career paths that a civil engineer might follow. First one I'm going to look at is environmental engineering. Now, at one extreme, you can think of, say, developing countries like Darfur, where you have a situation where you don't have fresh water, you don't have the basic necessities that we would consider. And a large number of environmental engineers, including members of our staff, regularly go out to developing countries, helping to put in infrastructure and plan for infrastructure. Closer to home, or even still in this, just to give you a few facts and figures, the bottom line is that providing fresh drinking water saves millions of lives every year. And it's very, very important. But closer to home, we also have problems that environmental engineers deal with, like trying to deal with the industrial contamination that even a country like Ireland has built up over the last 150 years. For many, many years, we didn't pay a lot of attention to what happened to toxins, oil-based products that leak into the ground that we now know are carcinogenic. Landfill sites weren't properly developed. So environmental engineers deal with all of this. And there's a lot of work to be done to actually clean up the environment that we already have, never mind protecting new works. Again, in the developing world, we're at a different sort of scale. I mean, this woman here is actually washing her clothes in that water. Sometimes the solutions are simple. In this case, this is a well in Africa where a simple act of capping the top of the well so that dirt and animal feces don't get washed back down into the well will protect it. And sometimes it's trying to find the appropriate technology that's most important. At another level, sometimes you need quite sophisticated solutions. So we're looking here at flooding problems. This also falls in under the umbrella of environmental engineering. So at the top there we have I think it was the M50 a few years ago, and I'm sure recently you've seen the shots of Dundrum shopping centre with the waters flowing into it. We're living with the reality of climate change, whether it's man-made or not. Climate change has always been occurring. So it's the engineering profession that really have to provide the solutions. We have to deal with the effects. Okay. Some engineers are also looking at means of maybe scrubbing the CO2 out of power plants and looking at other sort of techniques for capturing CO2 from the atmosphere. But on a day-to-day basis, we're the profession that will be putting in the flood defences, sea defences, trying to design. Recently, my colleagues and I put in a proposal in for EU funding looking at dealing with cold weather conditions on railways and roads. So it's the engineering profession that actually is at the forefront of trying to deal with climate change and at the forefront of developing things like wind turbine and alternative energy sources. If you are interested in engineering and have an interest in biology, you'll also find that environmental engineering deal with anything from composting, clever techniques for actually breaking down waste, to this picture here is one of Pollardstown Fen that a number of years ago a bypass was being put around Kildare. This is part of the main road down to Limerick, and the danger was that the Pollardstown Fen was going to be, the water table levels would be dropped, and that some of the flora and fauna that was only found in this region would be lost. I'll show you some of the actual engineering solutions to protecting it. There's also waste treatment. Now that's just a very quick snapshot of environmental engineering and doesn't really do the whole area justice. In transportation engineering, well, at one level, civil engineers actually put in the basic infrastructure. So these were some drawings of Terminal 2 before it was actually put in practice. So these were before a stone was turned on the site. All of these models had to be developed. An awful lot of work beforehand, trying to work out where do you put the facilities, how do you organise the flow of people in something like a railway terminal. And it's really transportation engineers, which are a subset of civil engineers, who provide that sort of function. Putting in ports, harbours. And then, in addition to the sort of physical infrastructure, you find that transportation engineers also look at control systems that are used in cities. So a lot of the people who'd be looking at the control systems would maybe have a particular aptitude for computer programming, logical design. You can get an awful lot more traffic flowing through a city if you optimize the allocation of the routes and set up very clever timing sequences in your traffic lights. And so any of the more modern citywide transportation systems will be monitoring the flow of public transport and controlling the lights. So it's actually quite a high-tech end of engineering. And of course, putting in new infrastructure like the Lewis. Again, then we'd have colleagues who are working in the developing world where transportation is vital, but at a very, very basic level. This is one of the main roads in Ghana, and I've shown you two photographs. One of this main routes just after a wet spell, so you can see the sort of condition that the roadway is, and then of course when it dries out, equally hazardous. So there's an enormous amount of work to actually be done on a sort of global scale. Geotechnical engineering, these are engineers who specialise in soil. So they're vital when it comes to any sort of construction project, because it's normally trying to get the building out of the ground is the difficult part. But also you might remember a few years ago there were some dramatic landslides over in the west of Ireland where, you can see here, the whole side of the hill simply peeled off and slid down, causing problems to the people living in the houses down below, and I think it demolished a bridge and blocked a road for a number of days. Those of you doing maybe physics or applied maths will appreciate what actually happened. A thin layer of soil overlying sort of a layer of rock. And basically the friction between the soil and the rock was reduced due to heavy rain, and the whole side of the hill simply slipped. So sometimes the calculations are relatively straightforward. There was a colleague of mine who was flown up by helicopter to look at this because they were still worried about some of the houses. Did they have to evacuate people or not? But relatively straightforward problem. Some calculations to see, was it stable, was it likely to continue to slide. This is a picture. It's a pity I don't have it as an actual video, but this was a whole hillside moving, with the trees moving at the same time. This was a bog again that got destabilized at around about the same period. And we have shots of it, the whole bog actually sliding down the hill. I showed you a picture earlier there of Pollardstown Fen. This was some of the geotechnical work that was done as part of the construction of the motorway. The basic idea was that what you're looking at here is an impermeable membrane that was put in, but then soil had to be put on top of that. The impermeable membrane was to stop this road simply acting as a drain and dropping the water table level into their town and the surrounding countryside for a couple of miles. So they tanked this cut, but then they had to backfill it with soil because otherwise the whole thing would have acted like a boat. And hydrostatic pressure on the bottom would have lifted it up out of the ground. So a clever piece of design. But it gives you an idea of the sort of scale at which civil engineering works are carried out. I mean, large-scale projects, a great sense of achievement when you've been working on something like this. And of course, Dublin Port Tunnel. Other members of our staff were involved in monitoring the vibrations while the tunnel was actually being constructed. And more typically, geotechnical engineers just really on some of the basement works. This was one of the buildings within Trinity a few years ago. Structural engineering, this is what we tend to think of as civil engineering as well. Large-scale bridges. Some of these ones are early models actually showing the Irish bridges before they were actually put in place. So you probably recognise some of them. Boyne Bridge, the Beckett Bridge across the, Joyce Bridge across the Liffey, and I think that's the Cable Stayed Bridge out at Dundrum. But these were all actually long before these structures were ever constructed. Lovely example in the UK of the Millennium Bridge, particularly interesting because it had all sorts of problems when it was constructed. That's another aspect of engineering in general. You're normally dealing with unique one-off projects, and sometimes things go wrong. And okay, you don't want your projects to go wrong, but the Millennium Bridge was a lovely example of how the engineers involved had to sit down. This bridge started to sway from side to side in an unexpected manner, and they had to go back to the drawing board very, very quickly, come up with solutions to fix it, and within a year or so they had managed to modify the bridge so that the problem was removed. But that's very much in the nature of engineering. Again, that is the Beckett Bridge, or at least an early model, and some of the finite element models that we had of it. Earthquakes, of course. I think the bottom story of that building has actually collapsed, and the whole thing has sat down. So an awful lot of engineers around the world working in earthquake engineering. You've probably heard about the demand for people over in New Zealand at the moment, primarily because of the problems in Christchurch with the earthquake there. This is the civil engineering test hall, and our students, as part of their studies, normally do a major sort of project in their final year. Those who are starting to specialise in structures will often do structural testing. You can get a sense of the scale of some of the equipment that we have. These are loading rigs that we use for testing full-scale concrete and steel beams and connections. Now, those are the quick run through the various areas, but some things that are common to all engineering sort of disciplines and all civil engineering disciplines. I'm just going to show you this little clip. What I want you to watch. Oh, hang on a second. I can get a. This is a stadium in Germany. Now watch the way, you can probably just see the actual stand is starting to vibrate up and down. There is a real example. You can imagine this is a sort of nightmare scenario for structural engineers. But these are the sorts of situations, these are things we need to design for. Designing something like that is quite complex. But it's just to give you a sort of an idea of the sorts of problems that we can have. Sometimes the most interesting problems are the ones where you look at a bridge and you find the bridge is gone for no apparent reason, and you have to try and go back and see what has happened. And our profession sort of develops through looking at these very rare failures to see how can we prevent them. This is a very famous collapse of, in London, the Ronan Point collapse, and the way in which we designed structures right across Europe and the world was heavily influenced by this particular collapse. Woman got up early one morning, went to boil her kettle. It was a very, very minor gas explosion. It blew out the corner of her flat. And like a house of cards, all the flats above, because her flat was on the corner, fell down, taking out all the flats below. And as a result of this, the investigations, we design buildings in a completely different way nowadays. There's a nice spectacular picture of a dam in the process of failing. You just maybe barely see in the top slide some little dark dots on the top. Those are large-scale bulldozers. They were starting to try and see if they could stop the dam being washed away, obviously unsuccessfully. The train crash you see there, that was actually the Armagh train crash where I think 89 people were killed towards the end of the 19th century. Had a massive impact on the way in which railways developed in Ireland, UK and Europe, and rail safety. The collapse of the Milford Haven box girder in the 1970s had a huge impact on the way in which we design bridges. And what I threw in the shot of the arch bridges all falling just for a little bit of drama. That was during flooding again, where it was one span had been washed away and a photographer knew the rest of the bridge was going to go and managed to get a camera in place in time. Now, one other thing I'm going to say, then I'll stop and there'll be a few minutes for questions. Some of you may be aware of the fact that to become a chartered engineer, by the time you graduate, you need to have a level 9 qualification. So I just very quickly wanted to say something about the way in which the School of Engineering at Trinity College has approached this. The standard degree and the degree that you'd apply for if you're filling out a CAO now is a level 8 4-year engineering degree. The Trinity degree has 2 years common. You have a free choice then at the end of the second year, and you go into either a civil engineering stream, mechanical engineering stream. Good chance there may be a biomechanical engineering stream for next September, an electronic engineering stream, or a computer engineering stream. As you go through, by the time you get to about third year, you'll be presented with another option that you may want to transfer and continue on to do a 5th year, so that by the time you leave college with a Master's in Engineering qualification, which is level 9, which is what's going to be required by Engineers Ireland. That's the accreditation body for you to become a chartered engineer. You don't have to follow that route. There will be the possibility of continuing on the 4-year program and maybe doing a specialist Master's in some area yourself at a later stage, maybe not even straight after your 4 years. So there's lots of different options, but just to say we are putting in an integrated 5-year program. That gives us a lot more scope, and it means that we're going to get to achieve the objectives of having a level 9 degree, which is to get everybody up to a very, very high technical level by the time you leave. In common with any of the other colleges, the way funding is set up at the moment is you would be required probably to pay fees if you follow that route for the final year in college. But who knows what will be the status quo by the time you get to fifth year. But just to say, while that will be an option, it's not the only option, and there might be very good reasons for leaving after 4 years and doing a specialist master's perhaps in a different university, or going on straight to research, doing a funded PhD. So lots of different options, but just something to be aware of. That if you're looking at engineering, you should be thinking now in terms of eventually you're going to need to get to a level 9, that's a master's level qualification. Okay, I think now it'd be a good idea to give you a few minutes to ask some questions, but if I don't get to answer your question, I will stay outside for a few minutes, so if you want to come up to me then. Or come along, we'll have a few open forum sessions where you can put questions, not just to me, but some of my colleagues from mechanical and electronic engineering. Any questions? Okay. Look, I'll be outside. Last word, just as I go through. Okay, I've explained the idea of the third, fourth, and fifth years, variety of disciplines. What should you have if you're, this is for engineering in general rather than just civil, but aptitude in mathematics, curious or inquisitive nature, adventurous, problem solving. Very much the sort of education we give you here is a problem solving education. So those are the skills that are being developed, and really upping your mathematical skills. Engineering is actually also quite a good qualification if you decide you're not sure what you want to do. Many of our graduates go into business rather than going into mainstream engineering, and financial institutions pick them up because of the problem-solving skills and numerical skills that engineers develop. So any engineer will have really, really sharp mathematics, good knowledge of statistics, probability, and this sort of problem-solving attitude. So you find that engineers end up, to a large extent, often working in management and working in a variety of roles rather than simply just as technician. Okay, listen, thank you very much for your attention.